Now, in the final topic regarding modes of convergence, we will give some special criteria for reversing the chain of implications for some specific cases only. So, the first lemma is that if the measure space is has finite measure, the whole space has finite measure, then the first part is that Fn converges to F pointwise almost everywhere is equivalent to Fn converging to F almost uniformly. And secondly, if Fn converges to F in L infinity norm, this implies that Fn converges to F in the L1 norm as well. So, of course, this implication we had already seen, and so this lemma says that when the measure space has finite measure, then the forward implication also holds, and this is precisely for the first part. This forward implication is precisely the statement of Egorov's theorem that we have seen. Egorov's theorem, which was precisely about almost uniform convergence when you have pointwise almost everywhere convergence. So, this we have already seen. Now, for the second part, if Fn converges to F in L infinity norm, then if you take the L1 norm of the difference Fn minus F, then this is nothing but the integral of Fn minus x, Fn minus F d mu, and this modulus Fn minus F is bounded above. So, this can be bounded above by the constant function Fn minus F L infinity d mu. This is because mod Fn x minus Fx is less than or equal to the L infinity norm. Outside of a null set. So, since the integral does not see the null set, we have this inequality, and now we can take this. So, let me rewrite this. D mu is less than or equal to norm of Fn L infinity norm of Fn minus F d mu, and now this is a constant function over on x. So, you can take this out of the integral. So, this is nothing but Fn minus F L infinity norm times the integral over x of the function 1, and this is nothing but the measure of x, and this is finite, and so this goes to 0 as n goes to infinity. So, in the finite measure space setting, we have seen a couple of reverse implications from pointwise almost everywhere to almost uniform convergence, and L infinity norm to L1 norm. Now, another special criteria is given by such so-called monic simple functions. So, these are called step functions in Tao's book. So, a monic simple function is a function of the form f equals alpha times the indicator function of E for alpha strictly positive, and E a measurable subset in X. So E is a measurable subset in X. And now we will consider sequences of monic simple functions. Now for a sequence Fn equals alpha n chi En of monic simple functions, assume that either alpha n converges to 0 as n goes to infinity, or there exists a constant c, positive constant c, such that alpha n is bounded away from c. So c is a lower bound for the alpha n's, and we also suppose as well that the measure of these mu En's is strictly positive for all n greater than or equal to 1. Now let's give some terminology. So I will call alpha n height of Fn, mu En width of Fn, and if you take the union of En for n greater than or equal to some capital N, this is called the nth tail support of Fn. So in analogy with functions defined on the real line, alpha n's, these coefficient alpha n's, of course I forgot to mention that these are all scalars, and so these are heights of the functions Fn. The measure of the sets En are called the widths of Fn, and the union of En for n greater than or equal to some capital N is called the nth tail support of Fn. So these are just some terminology that is being used here. So now we are ready to state our theorem. So this is the statement of the theorem, and the theorem states gives you characterization of this sequence of monic simple functions to converge to 0 in all these 7 modes of convergence in terms of these heights, widths, and the behavior of the nth tail supports for this sequence of functions. So the first one says that, for example, if Fn converges to 0 uniformly if and only if the heights alpha n go to 0 as n goes to infinity. Similarly, if Fn converges to 0 in L infinity norm if and only if the heights converge to 0 as n goes to infinity. So now we already see that we have seen that uniform convergence implies L infinity convergence, but here we can revert this arrow and have a if and only if condition when uniform convergence and L infinity norm convergence are equivalent. So this is for monic simple functions that satisfy these assumptions that we have stated. Similarly, Fn converges to 0 almost uniformly if and only if either, now we have two conditions, either the height goes to 0 or the measure of the nth tail support goes to 0. So here we have an either or two conditions. Then we have pointwise convergence if and only if either the height goes to 0 or the lim sup is the empty set. So note that this lim sup set is nothing but the intersection of all tail supports. So this is precisely n equal to 1 to infinity union n greater than or equal to n en. So this is the nth tail support. So in terms of nth tail supports, we see that the intersection of all nth tail supports must be empty, and we can similarly state it for pointwise almost everywhere convergence, which says that either the height goes to 0 or the measure of the lim sup is 0. Similarly, Fn converges to 0 in measure if and only if the height, either the height goes to 0 or the width goes to 0. And finally, Fn converges to 0 in the L1 norm if and only if the product of the width and height go to 0 as n goes to infinity. Now this is actually quite easy to see, the last one, because this is simply the L1 norm of Fn for each n. So this one is almost trivial. I will only do the cases for convergence in measure, so this one, and convergence almost uniformly, and the rest I will leave as an exercise. So let's see the proof for these two cases. So for the third part, we have to show that Fn converges to 0 almost uniformly if and only if either the height goes to 0 or the measure of the nth tail support goes to 0. So let's start with, for the forward implication, let's start with epsilon greater than 0, and so because Fn goes to 0 almost uniformly, this means that there exists a set E, a measurable set E, such that the measure of this set E is less than or equal to epsilon, and one can choose an n naught in n such that we have modulus of Fn x less than or equal to epsilon for all n greater than or equal to this threshold value n naught, and for all x in the complement of this exceptional set E, which has measure less than or equal to epsilon. Now we can deal with two cases. So the first case is that En is a subset of E for all n greater than or equal to n naught. So in this case, this means that mod of Fnx is equal to 0 for all n greater than or equal to n naught and x in the complement of E, because x does not belong to any of the sets En, and because Fn is equal to alpha n, the indicator function of En, this is going to be 0 for all n greater than or equal to n naught. And this means that, so this means that the measure of the union n greater than or equal to capital N En is less than or equal to the measure of E, which is less than or equal to epsilon for all capital N greater than or equal to capital N naught, and this means that the measure of the nth tail support goes to 0 as capital N goes to infinity. So in this first case, where you have all these Ens inside the set E, then we have automatically that the measure of the nth tail support goes to 0. Now in the second case, we have that x So En intersection E complement is not empty for some n greater than or equal to n naught. So in this case, this means that for x in En intersection E complement, we have that the modulus of Fnx is equal to the modulus of alpha n, and then this is less than or equal to epsilon for all n greater than or equal to n naught, because x belongs to En, Fnx is simply equal to alpha n. And so this is not for all n, this is for this particular value of n greater than or equal to n naught. But if epsilon is chosen less than this value c, so such that epsilon is less than c, where c was the lower bound for these alpha n's, then this implies, then this is a contradiction. So this implies that alpha n must go to 0, because since either alpha n goes to 0 or alpha n is greater than or equal to c for all n. Therefore, either we have the measure of the nth tail support goes to 0 or alpha n goes to 0, the height goes to 0. Now for the reverse implication, if alpha n goes to 0, so this implies by the first part of our lemma that Fn converges to 0 uniformly, and this implies that Fn converges to 0 almost uniformly. Now if the measure of the tail supports goes to 0 as n goes to infinity, we have to show that, so this so this is the second case, then Fn goes to 0 almost uniformly. So we will use this fact that the measure of the tail support goes to 0. So given epsilon greater than 0, choose n naught such that the measure of the union n greater than or equal to n, En, is less than or equal to epsilon for all capital N greater than or equal to capital N naught. So now if we set E to be n greater than or equal to n naught En, then for all capital N greater than or equal to n naught and x in E complement, we have that the modulus of Fnx equals F capital N x equals 0, because Fn does not belong to any of these sets En. X does not belong to any of the sets En for n greater than or equal to n naught. So this Fnx must be 0, and this implies that we have found that Fn converges to 0 almost uniformly. So now we are left with the fifth part, which is to show that Fn converges to 0 in measure if and only if either alpha n goes to 0 or the measure of the width goes to 0. So either the height goes to 0 or width goes to 0 as n goes to infinity. Let me start with the reverse implication. Now note that alpha n goes to 0 implies fn goes to 0 uniformly or even almost uniformly, as we have seen, and this implies fn goes to 0 in measure. So suppose that rather that the width goes to 0 as n goes to infinity, and in this case we have that if we set fn epsilon, so given epsilon greater than 0, if we set fn epsilon to be the set of points such that the modulus of fn x greater than or equal to epsilon. So then because fn can either be 0 or an, this implies that since fn x is greater than or equal to epsilon and this is greater than 0, this implies that x belongs to En. So this implies that fn epsilon is a subset of En, and so the measure of fn epsilon is less than or equal to the measure of En. So by the squeeze theorem, this means that the measure of fn epsilon also goes to 0 as n goes to infinity, because this goes to 0 as n goes to infinity. And of course these are all positive, so we get that the measures of fn epsilon goes to 0 as n goes to infinity, and this is precisely the condition for fn going to 0 in measure. So this proves the reverse implication. Now for the forward implication, let fn converge to 0 in measure. So let again fn epsilon be the set of points such that fn x is greater than or equal to epsilon. Now choose n naught such that the measure of fn epsilon is less than or equal to epsilon for all n greater than or equal to n naught. So this is a condition for convergence in measure. Now if again we are going to separate in two cases. So if an is less than epsilon for some n greater than or equal to n naught, choosing epsilon less than c implies that an converges to 0. So an, the other cases, so this is case 1, so the other case is that an is greater than or equal to epsilon for all n greater than or equal to n naught, which means that the set fn epsilon is precisely En, because this is positive and the set of points where fn is positive is precisely En. So this implies that the measure of En is equal to the measure of fn epsilon, and it's less than or equal to epsilon for all n greater than or equal to n naught, which means that the measures of these Ens, the width goes to 0 as n goes to infinity. So we see that in the case of simple monic functions, there are some reverse implications that we can state. Now as an exercise, consider the escapes to infinity example, example and the typewriter sequence in the light of this theorem, in the light of the above theorem. So you will see immediately which one converges to 0 in which mode by using the above theorem, and of course one has to also show the other parts of the theorem, which I left to you as an exercise. So this brings us to the end of the topic for modes of convergence.